we've been discussing state space representation, correct? We'll look at applying state space representation we'll discuss this in the context of examples. And we'll first discuss the translational system example. So let's say this is your translational system. So if you're given something like this, what you're going to do is, of course, you're not going to do this for this exam, because this is not part of test 1. But even if you're required to, let's say, find a transfer function, the first thing you're going to do is, right, Sammy? That's what you're going to do? Huh? So you have ds m1 s square k m2 s square f of s x2 of s and x1 of s. Okay, and you can easily write the equations of motion as for mass 1 you have, or x1, m1 s square plus ds plus k to x1 of s minus k into x2 of s is equal to 0. And the second equation is minus kx1 of s plus m2 s square plus k into x2 of s is equal to f of s. Okay. So this is what you do to do your transfer function, correct? And you can apply Cramer's rule to this to get your transfer function for either x2 over f of s or x1 over f of s. Now, this is, let's say, step 1. Step 2. Just looking at this, can you take the inverse Laplace transform of these two equations? So inverse Laplace transform would be m1 x1 double dot plus d x1 dot plus k into x1 minus x2 is equal to 0, right? And similarly, you're going to get m2 x2 double dot plus k into x2 minus x1 is equal to f of t, right? If you're comfortable with this, directly getting the differential form, you can do that. You can skip this step. Generally, the general procedure is to do this and then take the Laplace. But if you're following the impedance method, this is easier for you, right? So you can do this, write the equations of motions as Laplace transform and take the inverse and get this, okay? Now, the third step would be select the state vector or state variables. Now this is step 3. And you have to select minimum number of state variables, okay? And the selection should be state variables should be linearly independent. Okay. So minimum number of state variables, take this as 1, would be equal to order of the system. When you look at this, what is the order of this system? 2 into 2, right? You have 2 and there are 2. So it is essentially like a 4th order system. It's 2 into 2, okay? So how many state variables? 4 state variables, okay? In this case, this number of state variables will be equal to four, okay? And 2, you have to remember, if let's say for any x1, k dx or even just this is 2 into 2. 2 into 2. This is the second order differential. Yeah. This is the second order differential equation. This is the second order differential equation. So the system itself is a fourth order system. Okay. So let's do this. See, if you have Vi is equal to L into di over dt, you recognize that Vi and di are both variables. One is input, one is a system variable, right? If you're talking about an inductance, correct? If you can write something like this, these are not dependent variables, these are independent variables. How do you express it? For x1, x2, x3, x2 is equal to k1 x1 plus k2 x3. Here x2 is a dependent variable, but if x2 is equal to k1 dt plus k2 x3, you cannot quite say x2 is a dependent variable here. Linearly independent variable. You cannot express, this is not expressing something as a linearly independent. This is linearly independent. Okay? So x1 and x1 dot are not linearly dependent. Those are linearly independent variables. You see that? Right. Because there is a derivative. So if you plot, see, what does linear independent mean? You can always express something like this, right? So there's a linear relationship here. This is not a linear relationship because there is a derivative involved. So here, your x1, x1 dot and x1 double dot are independent variables. You have to remember that. Okay. So what we'll do is, as part of step 3, this is a note for you guys. So we'll choose 4 state variables, right? So for the 4 state variables, we'll choose x1 equal to x1, v1 equal to dx1 over dt or x1 dot, x2 equal to x2 and v2 equal to dx2 over dt or x2 dot. Okay. So these are my state variables. So my state vector X, the capital X, remember in the, can be expressed as X1, V1, X2, V2. These, so recognize what are the state variables and what are system variables here. What are the system variables? Remember how we define state variable? State variable is a linear combination of system variables. Okay? Huh? These are state variables. X1, X2, V1, V2. These are system variables. These mean displacement, right? This X1 and X2 don't necessarily mean displacement. They are state variables. They are mostly mathematical quantities. These are also physical quantities. Okay? So state variables are mathematical quantities. So what are these? These are also state variables. Do you recognize that? Sorry, system variables. Do you recognize them as system variables? They are velocities, right? Those are system variables. dx1 over dt or dx2 over dt, which is x1 dot over dot of t or x2 dot of t. Those are system variables. Those are physical quantities. Those are velocities, in other words. They are velocities, right? But on the left-hand side, those are system variables. So what in other words, what I'm saying is, you could have very well written this as Z1, Z2, Z3, Z4. And nothing would have changed. You see it? You can use any notation, I'm saying. System variables are physical quantities. You can identify them. Okay? Huh? X2 is displacement, X1 is displacement, right? X1 and X2 of t. Those are physical quantities. So if I write this as Z1, Z2, Z3, and Z4, nothing is going to change. You see it? You can use any notation for the state variables, but the system variables should be identifiable with this equation. Got it? Right. It has to be identifiable. System, you understand system variable? It's a physical quantity. Okay. State variable is mostly a mathematical quantity. State variable is a mathematical quantity representing a physical quantity. Got it? It's just used for convenience so that you can do math on it. And system variables, see, velocity is a differential of is a time derivative of displacement, right? But state variables are not. State variables are just algebraic quantities. Got it? There is no, you cannot take the integration. Once you form your state variables, they are algebraic quantities. They are algebraic variables. You cannot do integration or anything like that on them. For example, you cannot do integration on these because they are just algebraic quantities. Okay, algebraic variables. Got it? You cannot integrate these to get position. These are state variables. Those are velocities. So those are just another variable. Okay? Clear? Once you transform them into state variables, all your operations are algebraic operations on them. They are not calculus-based operations. Yes. This one? Yeah. X2 is equal to K1 dx1 dt. Right. So this is the state vector. Now you form the state equations. So step 3. Step 4 is state equations, right? For every state variable, you will need one state equation. Got it? Recall the general state space representation. What is the general state space representation? Let's recall general state space representation here. It is x dot equal to ax plus bu and y is equal to cx plus du. These are vectors, right? We have told. So we have identified this x. Okay? This is that x. Now x dot, we need to identify this x dot. So x1 dot is equal to x1 dot of t, which is equal to, so which one, you want to go with z1, z2, z3, z4 or x1, v1, x2, v2? Z1, everybody? You want Z1 or it doesn't matter? Huh? Okay, let's do Z, okay? So these will be, now we can change these to Z, or let's keep it X, this cap X, okay? We'll do Z1, Z2. So Z1 dot is equal to x1 dot of t, which is Z2, right? Z2 dot is equal to x1 double dot of t, which is equal to minus d over m x1 minus k over m x1 of t minus x2 of t. This is minus b over m x1 dot is z2 minus k over m x1 is z1 minus z3. just pay a little bit of attention here. It's actually, if you understand this, this is a very simple transformation. So you have, for every state variable, you need to come up with a equation. Okay? This is clear? Z1 dot. You need to come up with a, so what did we say? State space representation converts an nth order differential equation into n first order differential equations. Nth order differential equation. This is a fourth order differential equation. So it will convert into 4 first order differential equations. Got it? So we need one differential equation for every state variable. Make sense? There are 4. If you go by this, order of system equal to minimum number of state variables, right? So for each state variable, you generate one equation. All right. So this is the first equation. Z1 dot is equal to x1 dot of t, which is equal to z2. Z2 dot is equal to x1 double dot of t. Okay. Simple, right? I'll get the equation for this from here. From this one. X1 double dot of t is equal to, I'll move everything on the right hand side. Okay. So you get minus d over m, m1, right? Into x1 dot of t minus k over m1 into x1 of t minus x2 of t. You see that? There is m1 actually. All right. What is x1 dot of t in terms of state variables? Z2, right? X1 dot is Z2, X1 of t is Z1, and X2 of t is Z3. So I've replaced everything with state variables, all the system variables with. So the equation here is Z1 equal to Z2 and Z1 dot equal to Z2, Z2 dot equal to this. D m1, k m1 are constants, right? State equation. So what you're doing is you're taking the nth order differential equation and converting that to n first order differential equation. So if it's a fourth order differential equation, you need to convert it to 4 first order differential equations. Okay? And since you need 4 first order differential equations, each differential equation will be associated with a state variable. You see the correlation? If there are 4 state variables, you can associate 4 differential equations with them. Okay? So you got, for an nth order differential equation, you have n first order differential equation. So this is, do you see this as a first order differential equation? Right? Z1 dot equal to Z2, that's a first order differential equation. Z2 dot is equal to this, that's again a first order differential equation, right? So we continue with that. We need another, how many more do we need? 2 more, right? We have 2, we need 2 more. So can you guess the third? Can you guess the third? Z3? Z3 dot equal to Z4, right? Right. So Z3 dot is equal to what? x2 dot, correct? But that is equal to z4, all right? And finally, z4 dot is equal to what? x2 double dot of t, which is equal to, you use this second equation now, okay? It is minus k over m2 x2 of t minus x1 of t plus you have f of t, right? And this would be minus k over m2. What is this going to be? Huh? z3 minus z1, right? Plus f of t. Okay. So you have 4 equations. This is the first. Second. Third, and this is fourth. Huh? What? One minus two? It doesn't have to be symmetrical. You just have to look at this and figure it out. So x2 dot is equal to what? Minus k of x2 minus x1, k over m2 plus ft, f of t. So look at these 4 equations, and your step 5, what you can do is, so if you collect all of these, you're going to get something like this: z1, z2, z3, z4 dot 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 is equal to z1, z2, z3, z4 plus f of t. So look at this and look at this. Okay, this is our x dot. Can we write these 4 simultaneous equations in the form of a matrix? We can do that, right? So if you look at z1, z1 dot is what? z2, correct? 0, 1, 0, 0. Does this make sense? z1 is equal to z2. So how do you multiply matrices? You go this, right? So you get, if you look at z1, it is 0 into z2, z1, 0, 1 into z2. Got it? There is no ft term involved in z1 dot, so you put a 0 here, right? So now look at z2 dot. z2 dot is what you have. Is there a z1 term? Minus k over m1, right? So you get minus k over m1. Is there a z2 term? Yeah, there is, right? Minus d over m1 minus k over m1, right? Plus and 0. Got it? And again, what is the ft term there? 0. Z3 dot is Z4. So you're going to get 0, 0, 0, 1. Finally, Z4. Z4 is what? Is there a Z1 term? So it is minus K over M2. M2, right? Sorry, plus K over M2. Is there a Z2 term? There is a Z3 term minus K over M2, and then there is no Z4 term, right? It's 0. But, so this is 0. Here you have 1, right? Because you need that ft term. Okay? So if you compare this one and this equation, you see the similarities. So this is your x dot. This is the column matrix x dot equal to, this is that matrix A, the system matrix. Now can you relate why this is called the system matrix? Because all the properties are system properties, right? K, M1, D are system properties. You see that? K is the spring constant, M is the mass of the two elements, D is the coefficient, the damping coefficient. So you have A, this is X, plus B, this is the control matrix, right? And U is the input. That is what we said, control input or control vector, input vector. Got it? So the decom or the state vector is X. So U is just ft here. Okay? It's the input essentially. Now if we want to develop Y, okay, you will be given here, okay. In this, let's say the output, you are interested in x1 as the output. What are you interested in? Let me ask you that. What are you interested in? Displacement. Which displacement? Do you want both the displacement? Let's say you're interested in both the displacement, okay? You're interested in both x1 and x2. So your Y would be, see, you should always write this down first. This cannot change. This has to be the same, right? So you can write that down. You have Z1, Z2, Z3, Z4. Now if you are interested in both the outputs, both the displacements, you'll write 1, 0, 1, 0. Again, look at the multiplication of the matrices. So Y, the system output, is a linear combination of system variables. If you look at this, if you split this open, Y can be written as Z1 plus Z3, correct? You can write it as Z1 plus Z3, right? So this matrix form will give you that. It just depends on what are you trying to measure as an output? What is your interested output? If you are interested in both displacement and both velocities, okay? If you're interested in just x1, the displacement x1, got it? If you're interested only displacement x1, this is how you would write it, right? As the output, that is what you're trying to measure. Okay? For this course, this du term will mostly be 0. Okay? You will not be dealing with feed forward when you're talking about output. So this is your y equal to, this is the matrix C, and this is x plus du. So this is, forget about this. You'll generally just end up with y equal to cx. You just have to figure out what this C is all the time. So you will be specifically given, this is the output. Displacement is the output, or velocity is the output. Here, acceleration cannot be the output, because then you'll have to figure out another, you need more state variables if you're trying to measure acceleration. Correct? Because your state variables only give you position and velocity. Got it? So this is how you develop a state space model of a system. Yes. Let's say another couple of them, another two. Okay. Now, make an observation here. Everything on the right-hand side is an algebraic term. It's not a calculus term. Only this is the calculus term. Everything on the right-hand side of the equal to sign is just an algebraic variable, right? So you can apply, the reason you put it in state space model is you can apply a whole new set of tools to figure out. So what would be your goal here? Again, goal would be figuring out input-output relationship. That will not change. Okay? And input is very well defined. You just have to figure out what output you're interested in. And based on what output you're interested in, you can apply a different set of tools to figure out that output, input-output relationship. Right. If Z1 and Z3 is your interest, is your variable of interest. So how do we define output? Output is in terms of state space. I think you may not have looked into the definition. We discussed the definition in the class. So output is a linear combination of state variables, state and input variables. So here you will be given what is the output variable you're supposed to. What is your output variable? You'll be told what is your output variable. So accordingly you need to develop your state space model. So this is how you do the state space representation. Any questions, any concerns? Yes, again. This is a general form, right? We want to express it in this general form. Okay? Look at these as your variables of interest. Okay? You are essentially what you're trying to, ultimately, everything, this also leads to figuring out that input-output relationship. Here also, when you take the solution, right, when you do the particular solution, when you do the homogeneous solution, what are you trying to do? If you're given a differential equation, when you find the homogeneous solution, what are you trying to do? What is that homogeneous solution? Do you know? What is that? What does it mean? I'm not asking how you find it. I'm asking what do you mean by homogeneous solution? What does the homogeneous solution mean to you? No? It just means for zero initial conditions. So what does zero initial condition mean? If you have not applied any force here, okay, what is the output of the system, or what is the input-output relationship? Okay, if you are not applying any input, why do you say zero initial conditions? You are always given zero initial conditions, right? So when you equate it to zero, that means your initial conditions are zero. Initial conditions are zero means there is no applied input. Got it? When you do the particular solution, you are figuring out for a specific input, for a given set of initial conditions, what is the output. You're trying to figure out the output, yes. But for the homogeneous solution, you're trying to figure out what is the output when there is no applied input. Whatever the initial conditions are zero. If something is moving, it is moving. So at this, what does this represent? If I did this would be like a zero initial conditions. Okay. So what do we do? In case of this, so recall this. Can I erase this? This one? Okay. So think about this. You understand homogeneous solution and particular solution, right? You have some idea how to do homogeneous and particular solution. We have you know this representation? This is the transfer function, right? So in this case, it would be, what would it be? It would either be x 1 of s over f of s, or it would be x2 of s over f of s equal to sum n of s over d of s. So numerator of s over denominator of s. This is equivalent to homogeneous solution of the differential equation. This is equal to homogeneous solution of the differential equation. You see, this is a general output to input relationship. You haven't really specified what is this input. Now, if I give you that f of s is a step input, now what are you going to do to figure out you're going to do n of s, d of s into f of s. Now you're figuring out the output for a given input. This is like the particular solution. Understand? This is for zero initial conditions. No applied input. No? Huh? You don't see it? You have homogeneous and particular solution, right? Those are the two. A transfer function is homogeneous solution. You said homogeneous or general solution? It's homogeneous solution. So it's homogeneous solution. So homogeneous solution is equivalent to transfer function. The particular solution, you're trying to figure out the output, the response for a given input. Your system is not going to respond if you're not going to provide any input. But the input-output relationship will always exist, regardless of what input you're talking about. That is the system dynamics, that is the system property, right? So this can be a dynamic system, right? If you're not going to apply any force, there is an input-output relationship to this, which will always exist. So you'll think about what is the mass of this, what is the friction associated with each wheel, right? You're going to figure that all out. That is the input-output relationship. Now, once you start applying a force, it becomes a dynamic system. That time, you have to define what force you're applying or what input you're giving. And then you're going to talk about this, what is the displacement. But without that input, there is no point of talking about displacement. This will be a dynamic system. This will also, this is the input-output relationship. This is the output. You're talking about output for a given input. Your input can change. Input can be step input, ramp input. Those are the standardized inputs. So what you do is you develop a generic input-output relationship, regardless of what input you're applying to the system. And then you change your inputs and figure out how the response is. Got it? And that is what you do in homogeneous and particular solution. This will also allow you to do the same thing. It will just give you a whole different set of tools, whole different set of tools for doing that. And the biggest advantage is this applies to, your transfer function applies to linear time invariant systems only. But this is not limited to linear time invariant. Even if you have a non-linear systems, which you cannot avoid for aerospace systems. So most aerospace problems will be solved in this state space model. If you get to study more or if you go into advanced, this is how you'll see the model for any aerospace system. You will never come across transfer function. Very rarely are you going to come across transfer function, because then that will be a linearized version of the aerospace system. And you cannot really linearize. Think about linearizing an orbit, okay? If you're linearizing an orbit, you have to draw it like this. It has to be a polygon. Got it? It has to be a line polygon, and the system for each side is going to be different. The system equation has to be different for each side if you're dealing with this. But if you're dealing with this, you can just write one system model and use it to solve it. Because these terms can have those sine, cosine, everything here. It doesn't matter. Right? So let's move on.